In module 3.3, we defined expectation and variance of functions of random variables. And then we showed the examples of simple algebraic functions such as sum or difference of two random variables, product of two random variables, quotient of two random variables, and the formulae for them, assuming that the variables are independent. So what we saw there was that the formulae become significantly complicated when the variables are not statistically independent because of the existence of joint probability density function. In general, the joint probability density function becomes more and more complicated to estimate in practice when you have large number of random variables. So let's go back briefly and look at the derivations that we did. Not so much the derivations as the formulae we looked at last time. And the formulae that we looked at is expected value of a function phi of a random variable x and the variance of a function phi of a random variable x. And we saw that these formulae are natural extensions of expected value and variance of a random variable. And then we also saw that we could naturally extend the formulae for a single random variable to a function of many random variables, here 2. And that involves this joint probability density function, which is experimentally very difficult to obtain. In order for us to estimate expected value for any function phi, we need to know the joint probability density function between the random variables that are independent variables for this function phi. And it's therefore characterizing this joint probability density function is critical, and it's very expensive to do experimentally. However, it becomes much simpler if the variables are statistically independent, and that was the assumption that we made in order to derive the formulae for sum or difference, product, and quotient. And these are very simple functions. These functions that we have here are very simple functions. If we had more complex functions, these formulae are not useful, and we need some other method, and which we will discuss later on in the course. So going back, now what we will do today in this particular module, in module 3.4, is work through examples. The first example that we will solve is motivated by a bearing. So a shaft has a mean diameter of 1.048 inches, standard deviation of 0.0013 inches. The shaft is supported in a bearing with a mean diameter of 1.059 inch and a standard deviation of 0.0017 inch. What is the statistical variation of clearance is the question. And what we will do is we'll switch over to OneNote, derive the solution for this problem. So this is example 1. I'm going to pictorially describe the problem. So we have a bearing housing and a hole there. That's the diameter of the bearing. And a shaft. And we want to understand statistics of the clearance between the shaft and the bearing. So the shaft has a diameter d sub s equals 1.048 inches and a standard deviation given by 0.0013 inches. And the bearing has a diameter equals 1.059 inches and a standard deviation of 0.0017 0.17 inches. Okay. So this is my DS mean, and this is my standard deviation, okay, of the shaft. This is my mean value of dB, and this quantity is the standard deviation of diameter of the bearing. And what we seek is statistics of clearance, and let's call this clearance as some variable x, and this variable x is really the difference in diameter between the bearing and the shaft. And when I write an equation like this, since diameter of the bearing and diameter of the shaft are statistically uncertain, so is the clearance x naturally. So this is a equation between random variables. So what we now seek is the expected value of x, which is x bar, and that we know from the summation formula to be the mean value of bearing minus the mean value of the shaft, and that's equal to 0.011 inches. We also seek the variance of x, the clearance, which we know to be equal to s sub dB squared plus s sub ds squared. And if you recall from module 3.3, the variance will sum even if the quantities are subtracted in the mean value. The variance will always sum, and this was one of the important learnings from module 3.3. And this is equal to 0.0017 squared plus 0.0013 squared, and that's 0.0021 squared. And therefore, the sample standard deviation of clearance is 0.0021 inches. So that solves that problem. So in the second example, we have a simply supported beam with a circular cross section. The diameter is statistically distributed. Mean value is 20 millimeters. Standard deviation is 0.2 millimeters. And it's loaded by a bending moment, M, and that's also statistically distributed with a mean value of 100 Newton millimeter and a standard deviation of 0.001 Newton millimeter. And we are asked to determine the expected value of maximum bending stress developed in the bar. And we're given two hints. The first hint is that sigma, which is the bending stress in this simply supported beam, is defined as 32 m over pi times d cubed. And the second hint is the expected value of x cubed is the mean value of x cubed plus 3 times mean value of x times the variance of x. Okay. Now this is only valid if you have a normally distributed function. So we are assuming here that these distributions are all normal. So we will discuss this a little bit more in the next module. When we discuss normal distribution, we'll discuss the derivation of this formula. Okay. Work through this example. So we have a beam that is simply supported with a bending moment M, and the cross section of the beam is circular with a diameter d. And we are told that the max bending stress, which I'm going to call a sigma max, is 32 m over pi d cubed. And what we want is the mean value of this max stress. So let me call this sigma bar max, and that's going to be by the quotient formula. That's going to be 32 times the mean value of m, which is m bar. Recall mu of y divided by x, mu sub y over mu sub x for x and y, for independent x and y. So this is going to be 32m divided by pi times expected value of d cubed. And we have been given the expression for expected value of d cubed. So we can use that. So we can write this as 32 times the mean value of bending moment divided by pi times expected value of d cubed is d bar cubed plus 3 times d bar times s sub d squared. Notice how that there is this extra term, 3 times d bar times s sub d squared. That brings in the standard deviation of the diameter. So I can go ahead now, substitute the values. 32 times mean value of the bending moment is 100 Newton millimeter. We'll keep the units in newtons and millimeters here. And this will be pi times 20 millimeter cubed plus 3 times 20 times 0.2 squared. And you evaluate this, and this turns out to be 127.28 kilopascals. So with that, we worked a couple of examples on expectation and variance of simple functions. Here we had a quotient, and then we used another formula that was given to us for expected value of d cubed to solve this problem. So we'll end this module here.